So when we talk of implementing ensemble machine learning, we've had several videos or recorded sections on how to build ensemble, actually, theoretically. So we have videos on it, a lot of videos. So we are not going to go into too much theoretical basis of ensemble. But however, how can we implement it in WEKA? But as a matter of a kind of a short, maybe revision to bring back our memory to some of those concepts we covered during the presentation. So we're going to have a brief look at what is the machine learning building process. Then we look at what is ensemble on its own. Then we now move to how can we build it in WEKA. And we're going to start with very simple one, the voting ensemble, which is very, very simple ensemble techniques. There are several other techniques that we're going to be covering stage by stage. At the beginning, if we remember, so in some of our earlier videos, we have discussed this. Machine learning has a kind of an iterative building process. Iterative building process. Most important is to first of all get your data set ready. So once the data is ready, preparing the data set, you might need to do feature engineering, feature selection. So of course, this could be optional. The next is to do modeling. Use your algorithm to build the model. And then there's always, you check the performance measure. Is it doing fine? Is it up to the standard we are expecting? No, you can go back to the immediate one, which is modeling. Here you can start with hyperparameter optimization. Those are some of the discussion we had 2 weeks ago and the last week also, how to do hyperparameter optimization for our models. So you need to change the parameter of your models and see until you get the best performing model for your data set. Sometimes hyperparameter, maybe I started with K nearest neighbor. It might not be able to get you the best you want. You might need to change it to another, maybe decision tree. So maybe you need to go for support vector machine and also further machine learning algorithm we've discussed. So you might need to go back here also and change. So there's a kind of iterative process going on. You keep going back and forth until you get what you want. Sometimes you might need to go back actually altogether. Maybe to do more feature engineering. Maybe the features you have selected is not correct. Maybe you need to review them. Or sometimes you might need to go back altogether to look for maybe something is wrong with your data set. Maybe we need normalization and also further preprocessing we can do. Because the idea we let people realize is you don't need to spend all the time on preprocessing. Because no matter the amount of preprocessing you have done, you might still not be able to get what you want. In fact, in the course of doing too much preprocessing, you might miss the important information. You might kick them out. For example, I've seen people who go for preprocessing to the extent that they will normalize the data set before carrying out initial modeling. This is not supposed to be. When you normalize data, it means you are converting data to a particular range. The models might not be able to identify the hidden information in those data sets. Because we have seen a case whereby the original data got better result. When you normalize it, the result went down. So it means normalization does not always guarantee that you are going to get good result. So that's why preprocessing, a lot of preprocessing that has to be optional. So build the original data set, build the original model using the original data set, then go back. If it's not satisfying to you, you are not okay with the result, try again, do a couple of stuffs, get advice from expert to see what are the options I want to be. I can try out. I call this principle of let the data speak. Let the data speak. Yes. So you have done all the that let the data speak means you have to build the model using the original data, then do some preprocessing, normalization of the data set, try it again. After trying all this, sometimes you are not able to achieve what you want. So in that case, you have changed several algorithms from support vector machine, k-nearest neighbor, because in machine learning, it's always good to keep it simple. So you start from simple algorithm like KNN, decision tree. This is a very simple algorithm you can easily build. Your client can understand what you are doing easily. To more complicated one like support vector machine, And then maybe later you might need to go for even deep learning if we are working with images and videos. However, no matter the kind of, if you should try all models, depending on the complication, on how sophisticated the data is, or how hidden, or the nature of the data set. That's why I always say, let the data speak. You might have data set that is so hard to crack that there's no individual model you can try. The maximum they can get is maybe 70% for you, accuracy, or 80, but they don't achieve it. So in that case, we have to go for what we call ensemble. See, ensemble method is not something you just go for directly, because it's very, one, you spend a lot of time to build ensemble, so you don't go for it. And like I said, the principle of machine learning says keep it simple. Start from the simple algorithms, and then you go to complicated one when the simple ones fail. So before you go to ensemble, you must have tried several alternatives, simple one. However, if you are very deep and very complicated problem to solve, like some competition, or you want to ensure that you want to get good result always, ensemble is an ideal thing to go, even though it's going to take some time and resources, but I think it's worth it. So an ensemble of classifier is a set of classifiers whose individual decisions are combined to classify new example. So you have, in the ensemble, you have to build individual models, and then you combine them to take a decision. So you train like 15 models. They can be ordinary model from KNN, decision tree, support vector machine. It's always good to train heterogeneous ensemble. Heterogeneous means let the combining model be from different type of algorithms. Instead of having KNN trained 15 times, only KNN, changing the hyperparameters to generate new model. It's better to have 5 KNN, 5 decision tree, and maybe 5 support vector machine. So this is heterogeneous ensemble, in which case you are having different algorithms combined together to take a decision. So that mostly if you miss something in one, you get it in the other one. So this is a simple kind of revision on ensemble. Why does ensemble works? Also, suppose that you have 25 base classifiers, and each classifier has error rate of 0.35. So if we assume that the classifiers are independent, the probability that the ensemble classifier will make a wrong prediction is given as this. You can see from the error of 0.35, ensemble is able to take it down to as low as 0.06. So in reality, ensemble always guarantee that you're going to get better result than an individual models. And we have demonstrated in our theoretical class on this ensemble. We can check out the videos in the archive, in our YouTube channel, where we see several competitions. No single model ever won competition, like Kaggle international competition, like some company will bring out data set, very, very hard data. They say, okay, if you can improve our performance by 10%, then you're going to give you $1 million. So place $1 million on a particular, just to increase their present recommendation system by 10%. It's not a joke. So people came up with a lot of models. No one could reach 10%, 7%, 8%, until people came together, different groups from different countries. They combined their individual models to form ensemble, and they were able to beat that particular 10%. So ensemble has always demonstrated that it is better to use ensemble than using individual. However, when you use ensemble, there's some explainability that might be lost. You might not be able to explain the procedure to your client because it's going to involve a lot of mixing things together. At the end of the day, it becomes very clumsy. So, and also it takes a lot of time. That's why we ask to start from simple model. If a simple model can solve it and you get what you are looking for, there's no need to move to ensemble. You only move to ensemble when the simple one cannot achieve what you are looking for. So this is the general idea about the ensemble. So you're going to have your data set is there. So this same data set now, You are going to use it. You can break them down. You have seen different, create multiple data sets, build multiple classifier, C1, C2, up to CT, as many as possible. In some application, you might need to build like 255 individual classifier. Then you now combine them together. This is the combining, this is how you combine it. So once you build the individual ones, the individual could be homogeneous or heterogeneous. Homogeneous means they are the same algorithm. I have KNN where K is equal to 1. That is a model. I have another KNN where my K is equal to 2. This is another model. I have another KNN where my K is equal to 3. So as you change the hyperparameter of an algorithm, it generates a new model. So you need to generate such models as much as possible. Then, if all of them, they're of the same type, we call them homogeneous ensemble. Homogeneous ensemble. And if they are of different types, I train 5 KNN, 5 decision tree, 5 support vector machine, and then you keep combining different ones like that. This is going to be heterogeneous ensemble because it means you are combining, because the idea is that KNN has its own hypothesis space, H, where it works. It uses it to understand the data. So KNN has its own, SVM has its own. So no two algorithms share the same hypothesis space. So this is why it's good to build ensemble of different algorithms so that your data set will be looked at from different angles. The mistake of one algorithm might not be the mistake of the other algorithm. And by so doing, when you combine them together, the mistake of one will be nullified by the correct performance of the others. And we are going to see in an example shortly. So once we have this, then we have the combiner. The combiner can be bagging, in which case we just combine all of them together in a simple voting system. So we have 3 like 15 algorithms. So when we have new samples, this new sample now will be classified by 15 models. 8 of them said positive, 7 of them said negative. So we are going to go for positive. Majority carries the vote. This is bagging. So we have boosting whereby we give weight to individuals with more accuracy. Imagine I have a KNN that is having 99% accuracy when I train it, whereas this one is having just 85% accuracy. Why should I give this one 1 vote and also 99% 1 vote? It's like in a normal setting. You have a medical doctor of several years of experience, a professor of medicine. If they have to take a decision about a patient, either to go for surgery or not, the professor will be given more priority. If the professor said no, if 2 young trainee doctors say yes, they're likely not going to go for that trainee doctors. This is boosting. We give more respect, more votes to the opinion of excellent person. However, it has its own side effect in that if the professor make mistake, we are going to multiply his own mistake by 2. Because usually we give weight to it. Okay, if you have 99%, okay, you're going to have times 2. Your vote is times 2. If you have 80% times 1, see less than 85%, maybe you're going to have 0.5 weight. So we give weight to them. This is under boosting. We want to be able to give importance according to your accuracy. But then it has positive and negative. Bagging also has its own positive and negative. However, there are new ones that we call stacking. Stacking. This is where we don't vote, but rather we use the outputs to train another model to take the decision for us. So each of these we are going to see how to build around them. And like I said, this is just a kind of revision. We've treated the ensemble in more detail in our previous videos, so we can actually check them out in our YouTube channel. Now, so this is the same thing. Sometimes you have the data set, you have the base learner, we call the base learner, the individual models. Once you build them, the data set plus the algorithm, we produce a model. So we have different models. Now you have the ballot box. This is like simple voting ensemble. So when you have 10 samples, the 10 sample will be given to each of these guys, the final model. Everybody will say, hey, this is X, this is no, this is here, this. Then we can put them together and find our result. This is an example practically how ensemble works. You can see this ensemble of linear models. Even linear models that are considered to be very weak, if you do ensemble, it can get you 100% outcome. Look at this case. This is a linear model. This is a linear model. You can see this linear model alone was able to separate the data into, these are all negative. But here you have positive and negative this side. That's the power of this linear model. We build another second linear model, this one. It's able to separate this negative from positive and negative. We build the third linear model. By the end of that linear model, you can see that we are able to 100% separate positive from negative. This is the power of ensemble. An individual model cannot do it alone. In complicated data, very hard data. This is why we go for ensemble. So each of them, we take care of different aspects of it, and finally, we can get better result. So the value of ensemble has been demonstrated in real life experience. So when you want to count the number of beans in the jar, you put some beans in the jar. These are practical demonstrations that have been done. So you ask people to make a guess. How many beans do you think is in this jar? People make different guesses. We found out that when you combine all their guesses together, it's closer than any of them to the correct answer. These are real life demonstrations. We've also personally used to do this for my students in real life class. This balloon example. See, ask them to write their name in a balloon, the same color. Write your name, put them together, and then put in a basket. Go there and pick your balloon. Everybody, if you have 25 students, everybody might pick the balloon 25 times before reaching his own or our own. However, if you use ensemble method, ensemble says, let everybody pick one balloon, look for the name on the balloon, and give it to the owner. Within 1 minute or 2 minutes, everybody gets to the balloon. But if you want them to do it individually, it takes a lot of time. So this is corroborating the fact that the togetherness in group perform better than individual. And these are several real-life practical examples that are demonstrated that the ensemble perform better than individual. And also, this very popular diagram is often used. You see, when these are models. This model look at this big elephant from different angles. This one is looking at the tail. He said, hey, this one is actually it is a tree stump because it's only able to understand the leg. It's holding on the leg. This one say an elephant is a big snake because of where it is touching. Hey, what are you saying? It is like a sheet of a leather because of where it is touching. This one say, hey, all of you, you are wrong. It is actually like a little furry mouse because it's touching the tail. So each model will look at a particular data from the angle they are looking at it. So, but when you bring them together, so then you are able to get it right, especially on the principle of no free lunch. There's no algorithm that is always the most accurate in all situations. So generate a group of base learners, which then combine to get higher accuracy, and this has been demonstrated. So we have a model here, another model, another model. By the time you put them together, then you'll be able to combine, jointly take a better decision. So the ensemble gives global picture of what is happening. Each model will have a local understanding. No matter how powerful individual model, it's a local understanding of that your problem. So if you're lucky the problem is not complicated, a single model can model it and it will be fine. But in most cases, for complicated solution, no, you don't get an individual model to beat what you want to do. In that case, you go for ensemble because of its unique characteristics. So this is an example. You can see here, this is a random forest, this is logistic regression, this is KNN. This is an example of heterogeneous ensemble. We train this model, individual model, another model. So we bring a new case. This one say it is not a fraud. This one say not a fraud. This one say it is a fraud. So we have to vote. So you can see 2 against 1. So majority carry the vote, not a fraud. Now, a final example before we move to the practical demonstration of the symbol voting. When you look at this, this is an example of weather forecast. This is the actual data, the reality, the correct actual data. These are the prediction from model 1, model 2, model 3, model 4, model 5. This is the ensemble that combine them together. Now, the idea of ensemble is when we train this model 1 to predict if what is going to be the weather, is going to be cloudy or clear. The original one is, this is cloudy, it's clear, clear, cloudy, cloudy, clear, clear. You can see that this model is making a mistake here. Three mistakes. 1, 2, 3, 4, 5, 6, 7. Out of 7, there are 3 mistakes here. If you calculate the percentage, that's going to be like 70 something percentage. You see, percent. 70, maybe 70x percent. You look at this one also, 3 mistakes. Another 70 something is there. Look at this, 3 mistake again. But you can see that the mistake of this is different from the mistake of this model. This is the good thing about ensemble. Each of the individual model will be making different mistakes. So ensemble take advantage of that one. On each of them, this one has only 2 mistakes, maybe the one with the highest accuracy, another one also with 2 mistakes. You can see there is no single model actually that even got 90%. No, maybe the maximum will be like, this is 5 out of 7. 1, 2, 3, 4, 5. 5 divided by 7 times 100, you can do the math. So none of them is even near to 85%. They are like 70-something percent. Now, when we do the combination, this is ensemble. Ensemble was able, how do you do ensemble? You do voting. This is a simple voting ensemble. There are other ensemble that could be better by voting, but let's go for that simple one. Now, we look at, this is 1, 2, 3, 4. 4 model predicted cloudy weather, only one said no. So we go for 4 of them, majority. In this case, 1, 2. 2 said no, it is not cloudy. Sorry, it's not cloudy. Why this one say no? This is clear. 1, 2, 3. Majority carries the vote. Again, majority. 2 mistake here, majority. Majority, majority. You can see at the end of the day, this is the same like the original answer. Original answer, compare them, you can see. So in ensemble, we were able to achieve 100% accuracy. 100% performance measure. That is the power of ensemble. You see, even though each of them make at least minimum of 2 mistakes. However, because of the collaborative, the voting system, the mistake of this is different from this, is different from this. We were able to achieve 100%. So the only system that can guarantee you achieving 100% in machine learning is for you to go for ensemble. And sometimes the ensemble need to be really deep in the sense that you have to build several ensembles. Like I said, we can check out our earlier models, videos on how to build the ensemble, some of the theoretical basis behind it. Now, so now moving further, we're now going to look at a WEKA environment. How can you build a simple voting ensemble in WEKA? A simple voting ensemble in WEKA. How can we build that? What is the procedure to go about it? Yeah, so the individual models, we are combining together. Usually we call them weak learners. So weak learner 1, 2, 3. So as many as you can. The more the better, actually, especially if they are independent. You see, the more the better. So when you combine weaker learners together, they are going to generate majority vote that will ensure that you always get better results. So you combine multiple weak learners to make a very strong learning model, as we have demonstrated here, from 77, 78%, we were able to arrive at 100% from our experience and practice, and based on the principle of let the data speak. Ensemble has always achieved better performance compared to individual models. Now, to do that, let's go to let's demonstrate a simple ensemble in WEKA environment. As usual, you can see here, you have to open the Explorer. So I need to WEKA, go here, open the Explorer. Once you click Explorer, so then you can open it. Open the new one. So here you're going to open your data set. So open, we have data set here that we do use. Prepare your data set, put it in a CSV file format. So you have to change it to CSV file. Then let's look at customer Sean. So this is an example of telecom we've given in past also in our previous encounter, in our previous videos. This is a case of a telecom company that want to identify which customer might run away or not. So we want to determine if your customer is going to leave you early. You can quickly try to deploy some promotional sales for the customer not to go. So the earlier you do that, the better, because a lost customer is a potential enemy to that company, because it will badmouth the company to make sure the friend, the family leaves also, or they don't join that kind of a business. So the business world always now, they want to go ahead of the customer by quickly identify customers that are not happy and they might likely leave. So based on some of these attributes, they call it, want to see the churn customer that we not come or that will shun the system. The case may be. Okay. Just to be sure, we open the correct data. Customer shun, yeah. Yeah, so this is the correct one. Yeah. So the churn AS, this is what we want to predict. There are 483 customers that leave. These are the ones that left. 2,850, something doesn't leave. So this is a classification problem. We want to know if it's going to be good, they're going to leave or they're not going to leave. So once you load your data set, the next is go to classifier. So in the classifier, then here you have to choose, you have to decide how you're going to break down your data. You can now use percentage split. You can make it to be 70% for training, 30% for testing, and you can go for cross-validation. Cross-validation, where we already explained some of this also in our previous videos, how to divide data into cross-validation, tenfold. We can use fivefold because of time, depending on the size of the data set. Fivefold cross-validation, it means we are going to divide the data into 5 portions. We use 4 portions to train, 1 portion to test. The portion used for testing now will become part of the next training portion, another 4 for testing, remove another new one to be testing. You keep do that until you run the experiment 5 times using different portions to test the model. Then an average will be calculated for the 5 runs to know the performance of your model. This is the way. It's always good to start with that. So we are going to use cross-validation. You go to classifier. Under classifier, then you are going to see, you can see there are individual models now. You have the individual models. You want to do lazy classifier. This is our k-nearest neighbor. So we have selected k-nearest neighbor. We have done this one. Immediately run it, we are getting like 87% now. This is k-nearest neighbor, one of our very simple classifier. 87%. Now, this is still low. We always want 100% or close to that. So we try to do optimization of the parameter. K is 1. You can increase your K to 3 because it's 2-class problem. You make it to be 3. So run it again. So like I have recommended for us to watch our previous video, especially for those that are new, we'll get very simple to do actually. So you keep changing that. K is got to 5. You can see the result also will be changing. But then you get to a point that you cannot change it any further. You can see it has gotten to 89%. You have to check and get the best hyperparameter for each value. So once you get for K, then you have to also try for this one. You see, you have to try for the distance measure. The default value is Euclidean distance. You have to check for Chebyshev distance, Manhattan, Minkowski, and then you're going to select the best one that gave you the best result. Let's say Euclidean gave us the best result of 89. The best. So we have to take note of it because you have to do the optimization in the individual model first before you go and build Ensemble. Once we have run several individual experiments, we know the parameter that gave you the best result. Now we go to create the Ensemble. Go to A, you see this meta model. You click meta model, you can see there are different types of ensembles. we have the Adaboost, we have the bargain, we have. So for now, we are going to look into the simple vote. We want to start with simple voting method. There is stacking there also. So this stacking, you can build your own. Voting, you can build your own. There are some that already, they are built there on the automatic, originally built there. So for example, like random forest is already there. So, but here we want to build a simple voting ensemble. See, this is a simple voting ensemble that we want to build. Now, how do you build it? Now you have to click here, then you have to set your individual models. You have to set up your individual models in the system. So what are the individual models? You can see here classifiers. Here you have to define your classifier and add it one by one. See? So here you're going to say, this is where you're going to add your classifier. Here, click this. Add your classifier. So here you are going to choose which classifier you want. We want KNN, IBK. This is KNN. So you have to click here, set it. We got the best result using when K is 3. And if you need to also change this, you might have to change this. Included, maybe you got the best result using Manhattan distance. You have to take note. Okay. Now, you say add. You have added IBK. This 0R is usually added by default. I don't want it. So you can always, remove. You can delete it. You don't want it, you can delete. I've added IBK when K is equal to 3 and when the distance measure is Manhattan. Then I need to add another one. See, I'm adding another IBK, but this time I can change the value to be 1. So the moment you change the hyperparameter of a model, you are generating a new model. I mean, when you change the hyperparameter of an algorithm, the model generator is different from the previous one where K is 3. So I created this one to have K is equal to 1 again. That's why I said you must have check to see what are the individual model that will give you good results. For example, I have one K nearest neighbor with 89, another one with 90, another one with 88. They are in the same neighborhood of performance. Yes. The idea we want to use is the mistake of one is going to be different from the mistake of the other. So by the time you combine them in a voting system, they are likely going to give you better results than any of them as individual. So this is the idea of voting ensemble. So you keep adding more as you want. So I will make it to become 5, K to be 5. So add one again. This time around, I want my K to be 7. So keep add as many as possible, in as much as you have checked them and you see that they got something reasonable. And as I do that, you can also add another one. You can also add another one. Even though it is 7, I want to change the distance measure from Manhattan to be Minkowski. By so doing, you are generating a different model. So you have to have as many models as possible. Sometimes you might need to build ensemble of 255 models. And then this is all the same model. This is a homogeneous model till now. I don't want homogeneous, then I can go and add another algorithm. Let's say I want to add decision tree. You go here, you can add G48. It's one of the very popular decision tree. Add it to it, add it. Then you can move it up or down as you like. It doesn't matter. Anywhere you can see here, you can edit, you can delete anyone you don't want. So I want to add more J48. So as you add it, then you can always change the hyperparameter. The hyperparameter is the confidence factor. 0.25, I'm not going to make the second one to be 0.35. This is another model. So you keep adding and then adding until you are done with the number of individual models you want to use. Now, let's say I have 1, 2, 3, 4, 5, 6, 7. Now, 7. We can stop now, at least for the sake of demonstration. Now we are going to run our model now, the ensemble that we have built. We are now building an ensemble of 5 K nearest neighbor and 2 decision tree. You can add more, as many as you want. Now, why do we need to make it 7? Remember, it is voting ensemble. Voting ensemble that we want to build. So if it is equal, if you have even number, then you cannot vote because there can be a problem. If you have 6 during voting or for 2 classes, one can say it is yes, another will say no. 3 here, 3 here. We're going to have a tie. So we don't want to have a tie. That's why it's good when you are doing voting ensemble, you have to make sure the number of individual models is odd number so that we can vote to select the best possible. So once this is done, yeah, we have set up the ensemble. Yeah, this is okay. Now we have 7 ensemble there. You can see the number is there, 7. So, and then here we go. So we want to combine this ensemble in a very simple voting pattern. Okay, we have set the ensemble up. Check it, everything is there. Now 5 cross validation, 5-fold. You say start. Ensemble will start building. It's going to take time. This is one of the challenges of ensemble model. It will take time. You can see building 7 model. Now you can see now that even though we have not done deep parameter optimization for the individual model, the maximum we got from k-nearest neighbor was like 89, 80 whatever. You can see this one is already producing 92% for us. So if you do more ensemble, add more individual models to it, like 7 KNN, 7 decision tree, 7 support vector machine, you'll be surprised that you might be getting 100% performance fail. This is how we build a simple voting ensemble in WEKA environment. So I believe it's a good place to stop now. Thank you very much.